So I'm going to talk a little bit about some work I've been doing around forecasting using features of time series. So let me begin by just giving you some history about forecasting competitions, and then I'll talk about my contributions in these competitions a little later on. So forecasting competitions really began with the work of Makrodakis, Spiros Makrodakis, and this paper in 1982. The competition was run a few years before that. So I was about 12 when the competition started. I wasn't a participant. There's Spiros, who's since become a good friend of mine and a co-author. So this competition involved about 1,000 series taken from demography, industry and economics. The data was all either annual, quarterly or monthly, and people were invited to submit forecasts, which meant putting them on a floppy disk and mailing them to France, where Spiros and his postdoc, Michel Ibon, would analyse them, and then they published the results, who did best amongst all of these people that contributed forecasts. It was highly controversial at the time. There's some JRSSB discussion papers about it where people insult each other, and it's all recorded in the journal. So quite entertaining if you're looking to see one of these discussions. Then in 2000, at this stage I was sort of becoming interested in forecasting, but I wasn't a participant. Spiros and Michel Ibon published another paper on forecasting competitions. They called this the M3. The M stands for Makrodakis, the 3 because it was the third one. The second one was about another topic. And in this one, they had 3,000 series. Again, data taken from business, demography, finance and economics. Relatively short time series by modern standards. The longest one was only 126 observations. And they wrote, when they did this competition, this is the final attempt by the authors to settle the accuracy of various time series methods. So any academic who claims that their work is the final statement on the topic is crazy. And so Makrodakis, of course, has done an M4 since then, and is currently planning an M5 competition. So the M4 competition was run last year. By this stage, I was very heavily involved in the forecasting world. I was the editor-in-chief of this journal and helped Spiros set up the conditions for the competition. This time it involved 100,000 time series and much more variety of series than in the previous ones. And so I thought, well, let's see how well my methods do. This was the first one I'd really had an opportunity to participate in. So it was run from January to May. The data sets, the time series in the data were yearly, quarterly, monthly, weekly, daily and hourly data. So some of them are quite long, many thousands of observations long. The yearly data obviously is not so long. They were assessing not only the accuracy of the point forecast, but also the accuracy of prediction intervals. And a condition that, which I think makes it much more useful than the previous competitions, is that all people's code had to be public. If you were going to get awarded a prize, you had to have data that was public. Your code had to be public in whatever language you chose to code it. So 248 people registered, 50 people ended up submitting. I think the size of the data set was probably beyond about 200 of the original registrants, and they pulled out. The two winning methods which were announced in June, one was a hybrid of recurrent neural nets and exponential smoothing models. That was done by a chief data scientist from Uber. And the second one that I'm going to talk about today, the method that came second in the competition, was feature-based forecast combinations, which was submitted by my postdoc and me and a couple of other colleagues. Okay, so that's where the ideas come from. We're trying to forecast a very large number of time series completely automatically using some algorithm. And the idea is, can we come up with an algorithm that gives reasonably good forecasts across a huge range of different types of series? Okay, so let me cast back to John Tukey, who you will all either know his name or at least use things that he invented. He invented the box plot, for example, fast Fourier transform. He invented the word software, and the word hardware, and the word bit, and lots of other things that you probably use. What he's not so famous for is that he was my great-great-great-grand supervisor. So I sort of regard him as one of the family, even though I never met him. In a paper in 1985 with his fifth cousin, Paul Tukey, and who even knows who their fifth cousin is, but John and Paul got together and wrote a paper in which they introduced the idea, which they called computer-produced diagnostics, which these days we would call features, at least in the machine learning literature. Statisticians might just call them statistics. They're things that are computed from the data. Tukey, of course, was a statistician, but he liked to come up with his own words, and so he called these cognostics. So in a time series context, you might think of potential cognostics as things like correlation, size and direction of the trend, the strength of seasonality, when is the peak occurring, or more complicated things like entropy. So I'm going to use spectral entropy as an example here. So these are all things that you compute from your time series, and it'll give you a numerical summary of something about the series. Okay, so I'm going to take the M3 data as an example and look at some of the features from the data. So the period of the data is an obvious one. So this is the data annual, monthly, or quarterly? We have a measure of seasonality. So how strong is the seasonality in the data? If it's very strong seasonality at the seasonal, the seasonal measure is 1. If it's very weak seasonality, it's 0. And as you can see from the kernel density estimate for the 3000 series in the M3 competition, they're spread across all over the place. Plus, of course, a big spike at 0 for all the non-seasonal series. So a series at the left-hand end of that plot would be something that looks like that. A series at the right-hand end would be something that's pretty close to periodic. So this is a feature. We compute the feature, and we're going to use that information to inform our forecasting models. We have a similar measure of trend. How strong is the trend? So a series with very low trend would look like that. A series with very high trend would look more like that. Okay, so here the idea is that we take every observation in the data set, and every series in our data set, and we compute these features on the series. And then we want to be able to use this feature information to decide what sort of forecasting we should be doing. Here's another example. This is we do an STL decomposition on the series, then we take the residual, or the remainder components, and we compute the lag1 autocorrelation function for the remainder. And as you can see, you can get strongly positive and strongly negative autocorrelations. So a series with at the most extreme left-hand end looks like that. So those big spikes and troughs are inducing negative autocorrelation. And so the autocorrelation function of that series is going to be close to about minus 0.5. At the other end, very highly correlated series, almost looking like a I2 type series, where you've got very high autocorrelation in the remainder. Spectral entropy, it's a very interesting measure. It's a way of categorizing whether a series is forecastable or not. So is there a strong signal-to-noise ratio? So a series with very high signal-to-noise ratio has a low value for entropy. So at the left-hand end of that plot are the series which are the most forecastable, have the most signal in them and the least noise in them. So that series there came out to be the one with the lowest entropy in this collection. At the other end, you get series that are extremely noisy. So they're just, often you can't really tell the difference between them and an IID series. So they have high entropy, close to 1. So what we do is we compute lots of these features. I've just shown you a few of them to give you an idea of the sorts of features you get. You compute lots of these features. You can start looking at the feature space of the time series. Let me just move my mic to see if it stops cutting in and out a little bit. Try it up there. That's worse. Okay, so there's a graph of autocorrelation lag 1 against entropy. And so you can see that they're not particularly strongly related. There's a bit of a negative correlation there. But we're looking to find unusual series that maybe have characteristics that would lead to certain types of forecasting models. So you can see down in this bottom corner, you've got this little collection here and the other wall over there. So that suggests some series that maybe would use a different model there than we might use for series over in this end or over here. There's a graph of trend feature against entropy feature. So a much stronger relationship between these two. As you might expect, a series with very strong trend is going to have low entropy because it's got a very strong signal-to-noise ratio. So up in this corner here, that top left corner, a series which are highly trended. And at the other end of the plot down here, you've got series which have very low trend and high entropy, so they're sort of the very noisy, white noise type series. These ones over here are interesting because they have low trend but have quite strong, a sort of a moderate amount of entropy. So that would be interesting to sort of explore them. And you can start thinking of the space of time series as this large high-dimensional space which we're projecting down onto a few features, and then we can look at the features and explore what's going on. So this for lots of features of the time series. So here I'm just showing you 6 different features and different relationships between the features. So the graphs that I just showed you before were this one here, and it was, what was the other one I showed you? Trend and ACF1, which was this one here. But you can plot pairwise graphs of all of them. And we could look at more than pairwise as well. We could start doing, 3D scatter plots and looking at the various spaces. Okay, so first 2 parts of this, we have large collections of time series where we're trying to produce forecasts. And then the second part is we can take these time series, and for each time series we can generate vectors of features of the series, and we want to use those to help inform the way we do the forecasting. So now I want to show you a little bit about the types of algorithms that we're working on that use these ideas. So actually the features that I showed you are a very small collection compared to the numbers we use. So in the competition, the M4 competition, we actually used about 42 different features. So here are a list of most of them. So some of the ones I showed you, but also parameters from certain models, unit root test statistics, Arch and Gart statistics, a few others that we made up. We called things like lumpiness and spikiness and stability, which were to do with, does the series tend to have periods of high volatility followed by low volatility? We call that lumpy. Does it have periods where that's spikes occurring, but then it's relatively flat? We call that a spiky series. So we had ways of summarizing these types of characteristics into a few numbers. We end up with a vector of 42 features summarizing each of the 100,000 time series in the competition. So remember that the time series are of all different lengths. But our feature vector is the same for every single time series. The length of the series is just one of the features, but every time series is reduced down to a vector of the same length. Why these particular ones? Well, this has been based on a series of papers where we try different features and see what works. It's pretty ad hoc. Things that we think might be useful, we stick in. So the first paper I wrote on this was in a machine learning conference, an ICDM conference, with one of my PhD students and a guy from Uber, Laptev. The second one was with Kate Smith-Miles, who was well known as one of the chief investigators of ACEMS and a postdoc of ours, where we tried to look at, can you use features to see which parts of the space different algorithms work well? So that was published in the IGF a couple of years ago. And then recently, a paper with one of my PhD students called Meta Learning How to Forecast Time Series, where we looked at what features are the most useful for determining different types of forecasting models. So all the ones we've found useful, plus a few hundred other ones that other people have used that we thought we'd make available, are all now implemented in the TS features package on R. I was hoping to say now on CRAN. It's been sitting with CRAN for about 2 weeks. hopefully I'll soon be able to say now on CRAN. At the moment it's just on GitHub. Okay, so the first attempt at building an algorithm that uses these ideas we call the FORMS algorithm, which stands for Feature-Based Forecast Model Selection. The idea is you take a very large collection of time series, such as the M4 series or some other set of time series that you're interested in forecasting. We split that into a training set and a test set, and we compute the features on the training set. So we're going to pretend we don't know about the test sets. The test sets are the future part of the data, so the end of the data, and the training set is the first part of the data. The test sets are usually set to be the same length as whatever forecast horizon we're interested in. So if we're interested in forecasting 3 months ahead, then our test set is 3 months. Then we fit every forecasting method that we think might be useful to the training data. So we might have, in the example I'm going to show you, we had 9 different forecasting models. Some of them are quite general. So one of them, for example, was an automatic ARIMA model selection. So it fitted a model from the ARIMA space. Another one was exponential smoothing, random walks, neural networks, all sorts of things. And for every method that we fitted to the training data, we produce forecasts for the test data. Then we compute the accuracy of our forecast for every method to see which one did best. And then we label that series. So this series is one that neural networks do best on. This series is one that a ARIMA method did best on. This series is one that needed a random walk, and so on. And then once we've labeled the series, we can then train a random forest to identify, using the features, what was the best model for that series. The idea is that when we get a new series coming along, we don't want to have to generate forecasts from all the different methods. We want to say, oh, this series, grab some features, this looks like a exponential smoothing type series, so we'll go and do that. It makes it much, much faster. And we're working with companies like Amazon and Uber and Yahoo because they all want to do this really fast in real time. Yahoo, when I visited there a couple of years ago, they're forecasting about 100 million time series a week. And they want to, although they've got a zillion cores they can use, they want to make it really fast. So the idea is if we can find the best model as quickly as possible, then it saves them fitting lots of different models and doing computationally intensive work on every single series. Okay, so that was the FORMS algorithm. We submitted that to the M4 competition. It came about middle of the pack. Well, actually, about a third of the way down. So it's about number 15 out of 50. So not bad, but not worthy of a prize. The second one was we thought, well, let's take the same idea, but instead of getting a random forest to select the model that's best, let's find a way to weight all the forecasts and combine them. So we're using an algorithm to choose the weights for the forecasts. So if this algorithm says that this is obviously a random walk type thing, then it should give more weight to the random walk forecast and downweight the other ones. But we're going to do a weighted average of all the forecasts, and that's the final forecast for the series. So it's similar to FORMS, using the same feature inputs, but rather than a classification algorithm, we're actually trying to generate weights. So it's producing a vector of weights for each series. And so rather than the random forest, we use XGBoost, which is gradient boosted trees, very, very popular method in machine learning now. It was particularly useful for this context because we can modify the optimization criterion to be exactly what we want, and you can interpret the probability of the models being chosen as a weight in the combination forecast. So it was well suited to this problem, unlike a random forest which didn't have those features. So we trained it on the M4 data, as described before. But rather than saying which model is best, all we're trying to do is to say what are the weights that should be applied. Because it's very common to get two models that are almost equally good. And whether you choose one or the other doesn't really matter much. So if we take a weighted average of the good ones, then it should do better than choosing any model in particular. It reduces the variance. So the probability of each model being best was used to construct the model weights. So this took about 5 days of computing time. So remember that there's 2 stages to these algorithms. Building the model, either the forest or the XGBoost is a time-consuming process. It takes days of computing. But once you've built that, you can then forecast any new series extremely quickly because you've already know what the weights are just given the features. So the offline process is time-consuming, but once you've built it and stored your classifier or your XGBoost trainer, then it's very, very fast given a new set of series to generate the forecast. So we trained it on a temporal holdout set of M4, but we actually ran it on the full M4, and that was only a matter of a few hours of computing to do the 100,000 time series. So diagrammatically what's going on here is we take our series, we come up with some features, which there's 42 of them, I'm only showing a handful here. We run that through XGBoost to give us the weights. At the same time we generate 9 different forecasts from this series. These are then weighted using the weights out of the XGBoost algorithm, and that gives us our final forecasts. So on the M4 competition, there was a particular criterion that was used for accuracy, which goes by the initials OWA, which is, I can't remember what the O is, but weighted average of something or other. It was a weighted average of MAPE, mean absolute percentage errors, and MACE, mean absolute scaled errors. And so we were training it actually to minimise the exact criterion that was being used. So Slavek from Uber, his value was at 0.821, our value was 0.838, and the people third, who I don't know, they were from a private company, had a very similar to us. They're not statistically significant over the 100,000 series. The 9 models that are included in our forecast combination and in the forms algorithm, the selection one, are these ones. So some very, very simple things like naive forecast, which just means the last observation. Seasonal naive, which means the last observation from the same period. So if you're forecasting monthly data and you're trying to forecast February, then it's the last February that you observed. Random walk with drift. Theta method, which is the winner of the M3 competition. ARIMA models using the auto ARIMA algorithm forecast package. ETS models using an automatic exponential smoothing algorithm. TBATS, which combines trigonometric terms in a state space framework with Box-Cox transformations and ARIMA errors. That's a fairly complicated algorithm, but very adaptable. STL decomposition simply does an STL decomposition of the data and then uses an auto-regression on the remainder series and then adds back in, auto-regression on the seasonally adjusted series and then adds back in the seasonality. And then a neural network auto-regression uses lagged values of the series in an auto-regressive style, but with a neural network to do the modelling. So we can dig in a little bit to the results to see how this was working. So if we take our 100,000 sets of weights, so for every series, we have a set of weights, which says how each of the different forecast models should be weighted. So we have this matrix of 100,000 rows and 9 columns, the 9 weights for the different methods. And we can run that through a clustering algorithm to see, do the series cluster around different types? So we call these prototypes, so that each of the clusters, and in a k-means clustering algorithm, if we just took one cluster, then obviously we're essentially doing, every series has got the same weights, and they're pretty close to equal in weights. It's not like one method is getting stronger weights than others if you're giving everyone the same weight. As you add more clusters in your k-means clustering, we get different prototypes, which I'll just show you what they look like. So if we just had one cluster, or the first cluster in the algorithm, they have roughly equal weights. There's slightly more for some methods than others. So neural networks generally have the lowest weights. TBATS and ETS and ARIMA are a little higher, but they're roughly equal weights. And about 40,000 of the series clustered in this group. So a lot of series, you just took a weighted average of all the methods, you're going to answer a bit like this. There's another 20,000 series in group 2 for which a random walk with drift was quite strongly weighted compared to the others. So these are mostly random walk with drift type series. There's another 16,000 series for which an ARIMA model was strongly weighted compared to the others. And then there was another group. The next cluster was 13,000 series, and it was mostly TBATS type series. And then there was the next cluster was mostly STLM-AR type series. So the algorithm is quite efficiently choosing between the series, between the models, but weighting them equally if necessary, or combining weights where necessary as well. Okay, so R packages that implement this. The TS features package on GitHub will do all the time series feature calculations relatively quickly. The forms algorithm is on the GitHub page of Tianga Talagala, which is one of my PhD students. She calls it SIA. And the former algorithm, which is sitting on my GitHub account, is called M4 Meta Learning. We'll eventually put all of this into one of my forecasting packages so to make it a little more accessible, but at the moment it's all sitting on these various GitHub accounts. The papers on which this work is based, and there's probably about 5 or 6 of them now, are on my website, robjhyndman.com. And I just wanted to finish by mentioning all the people that have been involved in this work, including Kate and George, 2 academics, Pablo, Iro and Tianga, 3 PhD students, and Yan Fei Kang as a postdoc. Thank you.